Hi everyone. So in this video, I'm going to talk about 4 kinds of differential equations that you need to be able to identify them and solve them. I hope you enjoy. In this video, I'm going to give you an overview of what these 4 types are and the methods that we could use to identify them and solve them. So the 4 types of ODEs that we have is linear, separable, homogeneous, and exact. So let's talk about the first one. A linear ODE is given in the form y prime plus p of t times y is equal to g of t. This is the form of a linear ODE because it has the order of 1, because it's only the first derivative, so it has an order 1, and it doesn't have any of the special cases that we talked about in the previous video, where we can't have the function times its own derivative, or the derivative squared, or anything like a function of the derivative like log of y or y prime. These can't happen in a linear ODE. So we usually see, we can identify a linear ODE easily by sight if it has the following form. And how do we solve them? We solve them by using the integrating factor. So this genius mathematician, he was able to figure out an expression that if you multiply this expression by your differential equations and you use some calculus tricks by using the product rule, you're able to find a solution to your ODE. So very smart trick. And we're going to go more in depth in another video, going through the whole derivation and solving more examples to this. But simply, this is what's called the integrating factor. Integrating factor. Integrating factor. And this is what we use when we have a linear ODE. We just multiply it by the ODE, use the concept of product rule, and we're able to solve it. Alright, now let's talk about the second type of differential equation. The second type is a separable ODE. A separable ODE has the form n of y times dy dx is equal to m of x. So basically, it's hard to understand this form right off the bat, but basically it says that a function of y times its derivatives is equal to a function of x. Or in other words, we could write that a function of y times its differential dy is equal to a function of x times its differential dx. And the reason why it's so nice to have these kind of ODEs is because this is in function of y, this is in function of x, so we can simply integrate both sides and then we can find our solution. So basically, separable differential equations, we can identify them by trying algebra. We try to factor it out and have and separate the variables. That's why it's called a separable ODE, because we're able to separate the variables into function of y on this side, function of x on this side. And then our strategy to solve them is to simply integrate both sides, and then we can easily find a solution. The last two are kind of hard to talk about in this brief overview that I'm giving. But homogeneous is basically our strategy of solving homogeneous equations is that we're going to do a substitution of v equals y over x. And when we do the substitution, we're able to easily solve the problem. We can identify homogeneous equations by adding all of the power of the equation and having the same power. So I'm going to go more in depth on how that works, but just keep that in mind. Homogeneous equations usually have to do with, it has to do with doing the substitution, v equals y over x, and we can identify them by using the what's called the power rule of thumb, what Dr. Paulette told us, power rule of thumb. The last one is an exact homogeneous equation, and this one is particularly my favorite one because there's a test that we could use from previous calculus classes to test if the differential equation is exact. So there's a test involving partial derivatives. The test of exact ODEs is the following. When we have an ODE of the following form, so we have m of x and y, so we have an expression m as a function of x and y plus an expression n as a function of x and y times its derivative is equal to 0, then this differential equation is exact if the partial derivative with respect to m, the partial derivative of m with respect to x is equal to the partial derivative of n with respect to y. And if this is true, then the differential equation is exact. And there's a method of finding the potential function and solving the ODE. But again, I'm going to go more in detail in each one of these types of ODEs with specific examples and everything. So I'll see you next time.